Hi guys, welcome back to our discussion on infinite series. So in this video, we will discuss about comparisons of series. Specifically, I'll teach you how to use the direct comparison test and the limit comparison test to determine whether the given series converge or diverge. What we have learned so far are convergence tests that can be applied for series with fairly simple terms and those series with special characteristics. So in this case, a slight deviation from these special characteristics can make a test inapplicable. Okay, for example, in the pairs listed below, the second series cannot be tested by the same convergence test as the first series, no, even though it is similar to the first. Like for example, in number 1, given the series summation of 1 over 2 to the n, where n is from 0 to infinity. So this series is a geometric series, so we can determine whether this series is convergent or not. But in the second series, although this is similar to the first, but this is not uh, an example of geometric series. So we cannot determine whether this series is convergent or divergent using the geometric series test. In the second example, summation of 1 over n cubed, this series is a p series, but the second series is not. So uh, we cannot apply the convergence or divergence test using the p series. In the third example, the n term, a sub n, is n over n squared plus t to the second power. And as you can observe, this is integrable, so you can apply integral tests. But the second n term, b sub n, which is defined as n squared over n squared plus 3 quantity raised to the second power, is not integrable, no, using integral tests. Okay, in comparison test or direct comparison test, let summation of a sub k where k is from 1 to infinity and summation of b sub k where k is from 1 to infinity be series with non-negative terms. And suppose that a sub 1 is less than or equal to b sub 1, a sub 2 is less than or equal to b sub 2, a sub 3 is less than or equal to b sub 3, and so on and so forth up to a sub k is less than or equal to b sub k. So if as you can see, a sub 1 up to a sub k, these are the terms of the smaller series. And then b sub 1, b sub 2 up to b sub k, these are the terms of the bigger series. So in letter A, if the bigger series summation of b sub k converge, then the smaller series summation of a sub k also converge. And letter B, if the smaller series summation of a sub k diverge, then the bigger series summation of b sub k also diverge. So to use the comparison test, now you have to follow the following steps. So number 1, first you have to guess at whether the given series summation of u sub k converge or diverge. And then second, you need to find a series that proves the guess to be correct. That is, if we guess that the series diverge, then we must find a divergent series whose terms are smaller than the corresponding term of summation of u sub k. And if we guess that the summation of u sub k converge, then we must find convergent series whose terms are bigger than the corresponding terms of summation of u sub k. Okay, suppose you're given series summation of 1 over 2 plus 3 to the n, where n is from 1 to infinity. So our aim here is to determine whether this series converge or diverge. Okay, one way to determine whether this series is convergent or divergent is by using the comparison test or direct comparison test. So if the n term of the series is a rational form wherein the numerator is constant and the denominator is a constant plus the function, you can remove the constant so that this can be reduced to summation of 1 over 3 to the n, where n is from 1 to infinity. And this series is similar to this series except there is a constant in the denominator. And if you can recall, this series can be written as summation of 1/3 raised to n, where n is from 1 to infinity. That if the value of n is 1, then you have 1/3. If n is 2, then you have 1 over 3 squared, plus, and so on and so forth. And because 1 over 3 is common, so you can factor this out. So we have 1 plus 1 over 3 plus 1 over 3 to the second power. Okay, but this summation of 1 plus 1/3 plus 1/3 quantity raised to the second power and so on and so forth can be written in summation notation form as a summation of 1 over 3 to the n power, where n is from 0 to infinity, times 1/3. And because this is constant, we can place this inside of this summation notation, so that we have the summation of the product of 1/3 and 1/3 raised to n. But in this case, n starts from 0 to infinity. That if the value of n is 0, then 1/3 raised to 0, you have 1. If n is 1, then you have 1/3. If n is 2, you have 1/3 quantity raised to the second power, plus, and so on and so forth. And this is now of the form summation of a r to the n, where a is 1/3, r is also 1/3, and recall that if the absolute value of r is less than or equal to 1, then the series converge. So because this series is convergent, now we have to check which one is bigger. Is it the given series or the obtained series? So by comparison test, we compare the n term of the given series a sub n, which is 1 over 2 plus 3 to the n, with the n term of the obtained series, which is 1 over 3 to the n power. And because this series, because the n term of this series is, the denominator is bigger than the n term of the obtained series, which is 3 to the n. So 1 divided by this number is smaller than 1 over 3 to the n. So this concludes that this series is bigger than the given series. And because this series is convergent, then we can conclude that if the bigger series converge based on the definition, then the smaller series also converge. So from direct comparison test, we can conclude that the given series converge. Okay, the conclusion of the first example is supported by this figure, which shows that the sequence of partial sums of summation of a sub n is less than the sequence of the partial sums of the convergent geometric series summation of b sub k. So this is the bigger series, this is the smaller series, and as you can see, if the bigger series converge, the smaller series also converge. Okay, so in summary, using the direct comparison test, given the summation of a sub k and summation of b sub k, where k is from 1 to infinity, b series with non-negative terms, and suppose that a sub 1 is less than or equal to b sub 1, a sub 2 is less than or equal to b sub 2, and so on and so forth up to a sub k is less than or equal to b sub k. That if the bigger series summation of b sub k converge, then the smaller series summation of a sub k also converge. And second, if the smaller series summation of a sub k diverge, then the bigger series summation of b sub k also diverge.